All right, so we're going to look at how to calculate atomic mass, but before we do, I'm just going to go over again this relative abundance again and how that plays in the atomic mass. And so here I have an example of another problem. Boron exists in two isotopes, boron 10 and boron 11. Based on the atomic mass, which isotope should be more abundant? And so if I want to know which one's more abundant, I need to look at that atomic mass and figure out what is going on. And so I have 10.81. And so 10.81 is really close to 11. It's further away from 10. And so there must be more boron 11. Boron 11 is more abundant. Again, that's kind of like, I'll just do the math in here. So if you only had one of each element, so say that we had an equal amount of them, then if I were finding the average of this, I would say 10 plus 11 equals, and then since I had 2 divided by 2, and the mass comes out halfway in the middle, 10.5. Right? The same thing would happen if I had 10, 10, 11, and 11. So this time I'm looking at 4 atoms, 2 of them with a mass of 10, 2 with 11. The same thing's going to happen if I add them together because there's equal amounts on both sides. If I divide it by how many I have, it comes out to be 10.5. Well, what if instead I had 1 10 and I had 2 11s? And so I have things with a mass of 11 more often. And so typing in the mass of all those and adding them together, and then dividing by how many I have, I see that the average is 10.667, which is closer to 11. And that's because I have more of them. So what if I had 4 11s and only 1 10? I think I got all 4. And so since I have 5 this time, I'm going to divide by 5, and the average is 10.8. And so that's why it's skewing closer to 11, is just because I have more of them. And this is what the weighted average is going to take into account of. If I find more 11s in nature, that average is going to get pushed towards that 10.8. All right, and so finding atomic mass is fairly similar, except that we know percent abundance. So we don't know that there's 5 things with a mass of 11. Instead, we know it happens 4% of the time. And so to find the average mass, we're going to take the mass of our atom. And so if we're looking at lithium-6, lithium-6 has 6 protons and, well, I mean, 6 protons and neutrons combined. So we know that its mass would be 6 AMUs. And so it probably has 3 protons and 3 neutrons. Okay, we want to multiply it by how often we see it. I don't want to multiply it by this 4%. I want to multiply it by that 4% written as a decimal. And so that would be 0.04. So you're essentially just dividing that by 100 to get it back to its decimal form. Right, and so when I do that, I see that this would account for a mass of 0.024 AMUs. Right, I'm going to do that as well for lithium-7. So the mass of lithium-7 be 7 AMUs. I see it 96% of the time, and so 96% as a decimal would be 0.096. And again, I'm just going to work that out and find the mass that that accounts for. And when I do, it's 6.72. Right, I'm just going to take these two numbers and I'm going to add them together. And when I do, that's going to be my atomic mass, so plus my 0.24. And so it comes out to be 6.96 AMUs. All right, if we look at our periodic table, we should get an answer that's pretty close. And so some of these are based on some of these problems are based on just samples and not necessarily what we would normally find. And so, or they might just be made up problems. And so it should be really close to what's on the periodic table, but it might not match completely. Right? So I'll do another one here. And so let's look at iodine. Iodine is 80% of this. And so remember that that top number is our mass number. And so this is actually iodine 127. And so if it's iodine 127, we're going to say it has a mass of 127 AMUs. We see this 80% of the time. And so 80% as a decimal is 0.80. And so again, I'm going to work that out and find the mass. So 127 times 0.08, 0.8. All right, and so I see the mass is 101.6 AMUs. All right, my other isotope is isotope of iodine 126, so iodine 126. So the mass is 126 AMUs, and I'm going to multiply that by its percent abundance, which is 17%. And as a decimal, that'd be 0.17. So again, I'm just going to calculate that, and it is 21.42. And then my last isotope is iodine 128. So it has a mass of 128 AMUs. And it happens 3%. 3% is 0.03 as a decimal. And so I'm going to calculate that, which is 3.84. My last step then is to go ahead and add all of these together and get my atomic mass. And so I'm just going to add all of those numbers. See if I can get that to focus, sorry. And so I'm taking 101.6 plus 21.42 plus 3.84. And this is my atomic mass, 126.86 AMUs. All right, and again, looking at my periodic table, the atomic mass was reported as 126.90, and so we're really close. And so again, just looking at that, 126.86 is really close to 127. And if we see that, 127 is our most abundant, and so that's why that is closer to 127. And then it's on the low side of 127 because 126 is my next abundant. There's very little 128 to pull that average any higher. And so again, that percent abundance or the atomic mass will tell you what isotope is close to being, or which is being the most abundant in nature. All right, so that's all I got for you today. So hopefully the homework goes well. Again, if you need help, please, please, please ask me for help and jump on that Zoom session. So I hope you all have a great day. And if my computer cooperates, you won't have to awkwardly stare at me until I close this. But it seems like it is. Okay, here we go. All right, see you later. Bye.